All right, let's continue talking about hypothesis testing. So far, we know the first steps to formulate the null hypothesis and formulate the alternative hypothesis. And what do we do after that? So once you determine what your hypotheses are, here's the next steps. You need to collect a random sample of size n, right? So you would have to collect some data and you would determine your sample size. We'll talk about how to determine that later. And then off of that sample that you collected, you compute a test statistic, right? And I want to emphasize on this. This test statistic is going to be the key to make a decision about the hypothesis testing. Later, you'll see that. So this test statistic is the key thing. And you calculate that, and then the third step is to make a decision. So it's like a three-step procedure. You collect the data of size n, you calculate your test stat, and then you make a decision. How do we make a decision? We'll talk about it, but the outcome of the decision is one of these two. You either reject your null hypothesis in favor of alternative hypothesis, or you fail to reject the null hypothesis. In other words, you quote-unquote accept your null hypothesis. So you will hear this a lot, that the outcome is reject the null hypothesis or fail to reject the null hypothesis, and that's what it means. So here is the big picture of the process. Collect data, calculate, test the stat, make a decision. But to talk more about this, first of all, there are some assumptions that is the underlying assumptions of hypothesis testing. First is population is normally distributed, or if you're not sure about that, we need to collect a sample of size 30 or more. In that case, the central limit theorem kicks in and makes sure that the sampling distribution is normal. The distribution of x bar is normal. So one of these two needs to be in place. And then we also, for now, assume that the population standard deviation, sigma, is known. And you'll see where that comes into play. It comes into play when you're calculating the test statistic. So basically by now, you know your null and alternative hypothesis. Mu is equal to some mu naught. So the mu naught is basically the value that you're hypothesizing. In the GPA example, you were hypothesizing whether the average GPA is 3.0 or not 3.0. Well, that means your mu naught in that specific example was 3.0. So mu and mu naught can be sometimes confusing. To clarify here, mu is the unknown population mean that we don't know about and we will never know about because we don't have access to the whole population. And that's the exact reason that we're doing the hypothesis testing, because we don't know this. But mu naught is your hypothesized value, whatever you're hypothesizing in your test. So let's talk about this test stat. That is the key thing to make a decision. So this is the test stat right here, as you can see. This is the test stat. So you collect your data, you have a sample size of n, and at that point you can take the average of the sample, right? If you are doing the hypothesis test for the average GPA, you collect a sample of, let's say, 30, 40 students GPA, and that's your sample. The sample size is 30 or 40, whichever you do. Let's go with 40. So your n is 40. So right there, this is your sample size. And then using that sample, you take the average GPA of those students. That becomes your x bar. That is the sample average. And then your hypothesized value in that specific test, we were hypothesizing whether the average GPA is 3.0 or not. So this is your hypothesized value of the mean. And sigma is what I told you comes into play. That is your population standard deviation, which we assume it's known, or in practically we estimate that in applications. So having all those pieces, we can calculate this test a statistic, and we call this z-score. We call this z-score in our lectures. So at that point that we have the test-a-stat, the next step is to somehow make a decision using this z-score. First of all, this specific test is called z-test because the test-a-stat is z-score. And the reason is, if the null hypothesis is true, then this is a standard normal random variable. So we also refer to this test as a z-test because the test stat is standard normal. But in any way, we come out with an outcome of hypothesis test. We either, let me remind you, we either reject the null hypothesis or fail to reject, right? But in any case, our decision is really based on a sample size of size n, and if you end up accidentally with a sample that is not representative of the population, you actually might make a mistake. You make a decision that is not true. So there is a chance of making mistakes, or in other words, errors. So no statistical test is perfect because essentially it's based on a sample, and that sample might be a little out of whack, and you make the wrong decision. So what type of errors that can happen, right? This is what we want to talk about here. And we call them type 1 error and type 2 errors. The type 1 error is when you actually reject the null hypothesis, but the null hypothesis was not wrong. The null hypothesis is true. But you rejected it in your test. So that's a type 1 error. Type 2 error is failing to reject H0 when H0 is false. So that is another type of error. So the goal is to minimize these two types of errors as much as possible. So in this matrix, when your decision is fail to reject the null hypothesis and H0 is true, you didn't make any mistake, right? That's a good outcome. But when H0 is false, that's a type 2 error. And here is also no error. So now we know what is type 1 error, what is type 2 error. But in order to control these two types of errors, we introduce probability of type 2 error and probability of type 1 error. And we call them alpha and beta. So we're going to refer to these two as alpha and beta a lot. So make sure you remember what do they represent. Alpha is probability of type 1 error, beta is probability of type 2 error. Alpha is also referred to as level of significance. Level of significance of our test is also called alpha, but all it is the probability of type 1 error. So what was type 1 error? Was rejecting H0 when H0 is true. So alpha is probability of type 1 error, which is rejecting H0 when H0 is true. Basically, reject H0 given that H0 is true. A good thing about hypothesis tests is that we get to specify our alpha. So for any test, one of the things that you need to determine is what is the alpha of this test. And it's very important because what alpha does is determines when you would reject the H naught, when you would not reject the H naught. So what we're saying in hypothesis testing is that X bar, right, the sampling distribution of the mean or any sampling distribution follows a normal distribution. We talked about that using central limit theorem. Now, by determining the alpha, you are setting the rejection region and fail to rejection region, or in other words, acceptance region. Why? Because this area under the curve is alpha over 2. This area under the curve is alpha over 2 as well. Together they're alpha. So for example, if you set the alpha of your test as 5%, which is good, right? So you're saying I want to have a probability of type 1 error of 5%, which is pretty reasonable. That means this area is 0.025 and this area is 0.025. And if you notice here, this is the standard normal. This is Z. This is a distribution of Z. And if this area is 0.025, you can determine these values on the Z scale. In fact, this value is going to be Z of, we call it Z of alpha over 2, which is Z of 0.025. And this 0.025 refers to the area under the curve. And you can read that from the table. That is 1.96. And because normal distribution is symmetrical, this one is also negative Z of alpha over 2, so negative 1.96. So we just determined when we would reject our null hypothesis. When our testistat, so this scale Z is where our testistat is going to land somewhere here. So you calculate your testistat, Z-score, and if your Z-score ends up at any of these two areas, you would reject the null hypothesis. If your Z-score is between 1.96 and negative 1.96, you fail to reject the null hypothesis. And this is what this slide is about. You would reject the null hypothesis if your test score is more than Z of alpha over 2 or less than negative Z of alpha over 2. So the type 1 error is if your sample mean could fall in the critical region. So these two areas are called critical region or rejection region. Critical region is the exact term. Even though the null hypothesis was true, leading us to reject it, that's type 1 error. And then we have type 2 error, which means your test score lands here, but it actually should have landed somewhere in the rejection area. Your sample was not representative of the population, was oddly off, so you made the wrong decision. So these are type 1 and type 2 error, but what we want to do is we want to minimize these two types of error. We'll talk about them, but one thing that is obvious is the trade-off between type 1 error and type 2 errors. If we increase our alpha, right? If we increase our alpha, what are we really doing? Right? If we're increasing our alpha, we're essentially we're moving into this direction for the critical region. We are increasing the area of rejection. We're increasing the probability of type 1 error, essentially. But at the same time, we are decreasing the probability of type 2 error because we are closing this space and there's less chance of probability of type 2 error. And vice versa, if we decrease alpha, basically move these limits into this direction, we're decreasing probability of type 1 error because this area would be smaller, but we are increasing probability of type 2 error. So right now, if we get to specify alpha of our test, you realize that everything is in our control. So there's a power in our hand that we can manipulate the result. If I want to reject the null hypothesis anyway, I can make the alpha really big. Maybe I can make an alpha of 0.3, which basically set my alpha right here with a really big critical region, which really increases the chance of rejection. Right? So there is a way to manipulate the outcome of the test if any of the outcomes is your favorable outcome. But there are rules to select alpha. You cannot just select any alpha commonly. We can reject any null hypothesis if we set the significance level high enough. However, adjusting the parameters to a statistical test to obtain a desired result is unethical. So a good practice for choosing alpha is choosing an alpha, one of these values. One of these values are acceptable alpha levels, 0.1 all the way to 0.01. And whenever you're doing any hypothesis test, you would have to report your alpha. So the reader of the test would understand at what alpha level you make that decision. But always remember, if you are increasing alpha, you are increasing the type 1 error and decreasing type 2 error and vice versa. So this was the process of hypothesis testing. So first, we set up our H0 and H1. Then we collect data or collect a sample. And then we calculate our z-score. And then we determine our alpha, which basically gives us the critical region. And then we make a decision. By comparing the test-to-stat with the critical region, we make a decision. So this is the process of hypothesis testing. We'll work on some examples to make that more clear.